This is the first theoretical lecture of the week that starts on the 26th of April, and this lecture is the beginning of the third chapter, which is related with linear programming applied to project management. In this lecture, we are going to see how to model problems in linear programming. So we are going to use a case study to illustrate first how to formulate a linear programming problem, then how to use a graphical method to solve two-dimensional problems, and then we will introduce also the concepts of slack variables and the basic solutions. To illustrate the concepts of this lecture, we are going to use a typical production problem. So in this problem, we have two products, A and B. So they are from the area of tapestry. And to produce these products, we need two machines, machine 1 and machine 2. These machines are available the 12 hours a day for the first one and 14 hours a day for the second one. And we have also information related with the products. So we have information related with the profitability, which we measure through a variable that we call contribution margin. So contribution margin of A is 40 euros per unit, while contribution margin of B is 30 euros per unit. 1 unit is 100 square meters of tapestry. We have also information related with the technical requirements to produce 1 unit of each product. For example, in the case of product A, we know that the requirements in machine 1 is 30 hours per unit, and in machine 2 is 7 hours per unit. So in machine 2, 7 hours per unit. In the case of B, to produce 1 unit of B, we need in machine 1 4 hours per unit, and in machine 2 we need 2 hours per unit. So the first step for modeling this kind of problems is to organize the information. So we have this information here in the text, but we should organize it in a table like we have here. So we consider here in the columns the name of the products or the codes of the products. And here on bottom, we have the profitability, information related with the profitability of these products. Now, in the lines, I have here the machines, machine 1, machine 2, the availability of machines, machine 1, 12 hours a day, machine 2, 14 hours a day. And here we have the technical coefficients that we saw here. For example, to produce 1 unit of A, we need 3 hours in machine 1 and 7 hours in machine 2. While to produce 1 unit of B, we need 4 hours of the first machine and 2 hours of the second machine. The formulation of the linear programming problem involves 3 steps. In the first step, we start by identifying the objective of the problem. And to do that, we start to make questions like what is the goal, what we must achieve, what should we do. But in this case, in this problem, in typical production problems, the goal is always the maximization of the benefit of the production. And what is the benefit? The benefit is simply the contribution to the profit of the company. And we can simply say that it is related with the sales and the cost of sales. The second step in the formulation process is to identify the decision variables. So the decision variables are quantities or properties that can be controlled by the decision maker. Of course, that they must contribute to achieve the objective, and they are going to be used to build the problem. So in this case, for example, to express the benefit, we need the contribution margins of each product, but we need also information about the quantities that will be produced. So we are going to define x1 and x2 as our decision variables. X1 represents the units of product 1 that will be produced, and product 1 is product A, and x2 is the units of product 2 that will be produced, and product 2 is product B. And in the third phase, we start by writing the problem, writing the expressions that define the problem, and we start with the objective function. So we are going to look with more detail to the benefit. So we stated previously that the benefit was the difference between sales that we are going to represent by V, and less the cost of sales, which we are going to represent by C. But we are going to split the costs in two parts. One that we call variable costs, and another one that we call fixed costs. So variable costs are costs that depend on the quantity produced, for example, raw material. Okay, while fixed costs is, for example, the maintenance of the machines, or the rent that we pay for the building. So they are more or less fixed. Now, in this way, we can define this quantity MC, which stands for total contribution margin, which is the difference between the sales and the variable costs. So this means that we can rewrite the benefit as we show here, that is the difference between the total contribution margin less the fixed costs. And this is important because the fixed costs are a constant. So when we want to maximize a function B, which is the same to maximizing only this part related with the contribution margin, because this is a constant. So we can maximize only the total contribution margin. And in this case, the total contribution margin, of course, is the contribution margin due to product 1 and due to product 2. Okay, so we are going to define an objective function z, which we want to maximize, which will include the contribution margin of the two products. Okay. Now let's look to another concept, the concept of a unit contribution margin of, or simply the contribution margin of a product. So it's defined through the price of the product. So we have the price of the product, and we need also the unit variable cost of the product. For example, the cost of the raw material used to produce one unit. And then we have the contribution margin of the product, which is the difference between the price and the variable cost. This is the information that is given us in the beginning. So in the beginning, the data of the problem included information about the contribution margin of each product. Now, in this way, having the information about the contribution margin of each product, we can define the total contribution margin of that product, which involves the unit contribution margin multiplied by the number of units that we are going to produce. So in this way, we can identify what is known as the objective function for this problem. So the z is simply the product of the unit contribution margin by the quantities of each product. So contribution margin of product 1 was 40. The quantities that we are going to produce is x1. And for product 2, we have 30 and x2. So this is what we want to do. We want to maximize this function z, which is 40 x1 and 30 x2. We need also to consider restrictions. Restrictions are limitations related with the situation which condition the implementation of the project. So in a typical production problem, the limitations can be the scarcity of resources, they can be related with the supply and the demand. For example, in the case of the supply, we may have insufficient space to store raw material. In the case of demand, we may be unable to sell all of our production. We may have also capacity limitations, and we have also in general conditions related with non-negativity of variables. For example, the quantities cannot be negative. So in the problem that we are trying to solve, we essentially have the scarcity of resources. So the number of hours that we can use in each machine is limited. So this kind of restrictions can be stated in this way. What we are going to use cannot exceed what is available. So this is what we need to consider. Let's write the restrictions, and let's start with the machine 1. We saw previously that the requirements to produce A and B in machine 1 was 3 hours of A and 4 hours of B. Now, the amount that we are going to produce of A is x1, and the amount that we are going to produce of B is x2. So this is the number of hours needed to produce the amount of A, and these are the number of hours needed to produce the units of B. So this is what is here. So this is what we will use. Okay, and this is what is available. And we have here the first restriction. Okay, in second machine is the same. So we have here the requirements 7 and 2. So what we are going to use to produce A and to produce B, and this is what is available. And then we obtain the problem formulated as we present here. So we start by presenting first the objective function z, which in this case is the total contribution margin for the production of 1 day. That is, this is in euros per day. We must state what we want to do with this function. That is, we want to maximize it, but we want to do this subject to certain conditions. We have here 2 restrictions, okay, which represent the limitations of the machines, that they are available a certain number of hours a day. And we have also here the information related with this with the variables. That is, they represent units and they cannot assume negative values. They can be real quantities because the production in 1 day can be incomplete. So we can start one unit today and finish it only tomorrow. So this is units per day. Now we are going to show how to solve this problem using the graphical method, which we can use for 2-dimensional problems. So to apply this method, we need to identify the solution domain. So we need to draw a graphic in which we have the 2 axes, x1 and x2, and we need to identify the solution domain, which we do in this way. So, for example, for restriction 1, we need to identify the boundary that restriction 1 defines. And to do that, we need to identify the points in which the boundary of restriction 1 crosses the axis. So this is the boundary of restriction 1. So we change the condition. Instead of less or equal, we consider equal. So in the boundary, what we are using is equal to what is available. And to identify this point here, the point in which the boundary crosses the horizontal axis, we consider x2 equal to 0. That is, if this term is 0, we get x1 is 12 divided by 3, that is 4. So this point here is 4. And we do the same for the vertical axis. In this case, we obtain 3. Okay. Now, in the case of restriction 2, we do something similar. So we need to identify these points here, this one and this one. So this is what we do here. So the boundary of restriction 2, the horizontal intersection is obtained with this condition. That is, we get 2. Okay, here, and the vertical intersection, we consider x1 equal to 0, and we get 7. So this is 7. Okay, so this is the solution domain. So with the objective function, we do something similar. We want to draw what is known as isolines of z. So, and we start with the simplest one, z equal to 0. So z equal to 0, if we consider x2 equal 0, we will get x1 equal 0. That is, it's this point here. So to draw a line, we need another point. For example, if we consider x1 equal minus 3, we will get x2 equal to 4. And we have here a second point. So minus 3 something like here, and 4 something like here. So we can draw this line. Okay. With these lines, we can extract more information that is useful. So, for example, if we rewrite these equations in this way, we can extract this coefficient, which represents the inclination of the lines. For example, in the first one, the inclination of restriction 1 is a negative 1. It's minus 0.25. In the case of restriction 2, we get minus 3.5 for the inclination. And in the case of the lines of z, or isolines of z, we get minus 133. So, and we are in conditions, with the information that we get, we are in conditions to identify the location of the optimal point. So we have the initial isoline of z. We know that they grow, all isolines grow in this direction. So we just need to start to consider isolines until we find one that still has a point in the solution domain, and which is highest than the previous ones. So this one identifies the optimal, and its value corresponds to the value of the objective function in the optimal point. So we can also confirm from the analysis presented before, that is, we identify the inclinations of the lines involved in the definition of the optimal, and the optimal, in the optimal point, we have this relation. The lines of z are between the lines that define the optimal. In this case, the intersection between restriction 1 and restriction 2. Since we identify the lines that define the optimal point, we just need to solve now this system of equations to get the coordinates of the optimal point. And with these values, the optimal values of x1 and x2, we can evaluate the maximal value of the objective function, which we get this value in euros per day. Now we are going to introduce the concepts of slack variables and the basic solutions. These concepts are necessary to reformulate the problem for numerical solution, which we need if we have more than two decision variables. So instead of writing the restrictions in the way that states that resources that we use cannot exceed the resources available, we can write them in this way. That is, resource used, what we use, and what we don't use is equal to what is available. In this case, we have here what we use. This is what we are not going to use, and this is what is available. So this part, so we can write the restriction this way, introducing two new variables, x1 and x2. So these are the slack variables, and they represent the resources that we don't use. So let's look now to the concept of basic solutions. With the transformation that we show before, the restrictions become equations, and in that case we have a system of two equations which can be used to obtain solutions. The problem is that we have more variables than equations, so the system is possible but is undetermined. Nevertheless, if we set two variables equal to 0, the solution that we can obtain is called a basic solution. And what can be shown is that, in fact, the vertices of the solution domain are basic solutions. We also know that since we have only linear expressions, so the linear problem will have a solution in the boundary. That means the optimal is a basic solution, and this is the base for the numerical method that we will see in the next lecture. We are going to check now in the case study that the vertices correspond to basic solutions. So we have here our system of equations, and to obtain a basic solution we need to set we have 4 variables, so we need to set 2 variables equal to 0. So these variables that we are going to set to 0, we are going to call them non-basic variables. The remaining variables, that is the ones that can be different from 0, we call them basic variables. So let's check the first vertex, the point in which x1 and x2 is 0. Of course, that we know that the solution in that point, so which we call point 1, so solution of the decision variables is 0, 0. And if we consider x1 and x2 0, of course that the system of equations will give us this solution s1 12 and s2 14. So for this to be a basic solution, we need to consider 2 variables equal to 0, that is in this case x1 and x2, that is the non-basic variables, and with this choice we get this set of basic values, that is, we can extract the solution of s1 and s2. Okay, this is what we have here. We also have here the information of the objective function at this point, which is 0. So this is the first point, and it is a basic solution because it is obtained by setting. It can be obtained by setting 2 variables equal to 0. These two, x1 and x2. The second point that we are going to check is this point here. So what we know about this point is that x1 is 0, and we are in this line, in line 1. That is, we are in the boundary of the resource number 1. That means that s1 is 0. So these are my non-basic variables. If I use this condition, I will get my basic variables, the value of my basic variables. So I will get x2, which we know from previous calculation that is 3, and we will get the value of s2. because we are far from this restriction, so S2 is greater than 0. And if we use the system of equation, we obtain the value 8. We can also evaluate the value of z in this point because we know the coordinates of the decision variables, and we get, in this case, 90 euros per day. The third point that we are going to check is the optimal one. So in this point, we saw previously that we have S1 equal to 0 and S2 equal to 0. That is, we are in the boundary defined by the two restrictions. That is, what we are using is equal to what is available. So this implies, of course, setting this condition in the system of equations, we will be able to get the values of x1 and x2, which are listed here. So 145 and 191 units per day. So with these values, we can also evaluate the value of the objective function in this point, which is 115 euros and 45 cents. Now, this is also a basic solution because it can be obtained from the system of equation setting these variables equal to 0. And now we are going to check this point here, which is the last one. So what we know about this point is this. So we know that x2 is 0, and we are in line 2. So in line 2, we are using the resources completely, so we must have S2 equal to 0. So these are my non-basic variables. If I set them equal to 0, I can extract the value of the other two. So x1 we already know that is 2, and we will get the value of S1 because we are far from this boundary. So S1 must be greater than 0. And in fact, if we use the system of equation, we will get S1 equal to 6. If we use the coordinates of the optimal point, we get the value of z in this point as 80 euros. So this allows us to confirm that in the optimal point we get the maximum value of z, which was 115 euros and 45 cents. So another way to find the optimal is to evaluate the value of z in each of the vertices and select the maximum value. And this is the end of this lecture. Thank you for your attention and see you on the next one.